All right, good morning, everybody. Let's make a start.
Somebody put their stuff there on meetings.
So the usual quick check-in. How is everybody doing? Existing? I like it. Okay. Anyone doing better than existing?
No.
No. Okay, that's fair. Yeah? Awesome. Nice. I like it. All right. So, the next thing is a quick check-in on the course. Any questions, queries, complaints, comments? Okay. So I will put up information about the midterm a little bit later in the week, but the basics are it will cover everything in weeks 1, 2, and 3. It is written, so you'll need to write down maths. There might be 1 or 2 multiple choice questions, but most of it will be stuff where you're doing working. This is so that I can give you partial credit, even if you don't get to the right answer. I won't ask theory questions, so I will never ask you to prove any of the theorems that we kind of whip by. There will be a formula sheet. I will need to update the one that's currently on Canvas because we will get a little bit further than we did last year. So the one on Canvas is good, except it doesn't have anything about double integrals, which is what we're covering today. So I will update that. You can also bring in one A4 piece of paper with whatever notes you feel that you need. Calculators, any calculator goes. I don't care. I try to set exams where you don't need a calculator, but if you don't feel comfortable unless you have one on your desk, that's fine. Yes?
Maybe one question. The A4 sheet of paper on one side or both sides?
Both. Yeah. No. That's both sides. Yeah. A4, both sides. Okay. Any other questions? Yeah.
Are we gonna be expected to understand graphs or be able to not plot but to if you give us an equation sort of the quizzes that we have at the moment?
Okay, so I will try. So the question is, do you have to understand graphs? Like if I give you an equation, do you need to know what it is?
Or what we covered last week, what was it called? Curves?
Yeah, so you need to cover. So I will never ask you to sketch a complicated 3D graph, because that would be cruel and unusual. But I might ask you to, for example, I might give you an equation and say which of the following graphs does this equation belong to? So that kind of thing. Does that? Okay, I'll try and be a little more specific in the Canvas announcement, but you can always just ask me. Okay, I will ask you to integrate some stuff, but I'm not going to ask you the crazy stuff that you might have encountered, and you'll see in today's tutorial there are a couple of crazy integrals. Don't get hung up on them. Okay, the integrals are not the point. What I wanted you'll see in today's tutorial is for you to be aware that integration can get quite hectic, but mostly today we just do it numerically anyway. So don't get hung up on the integrals. Notice what it is that we're doing when we're integrating. Yes?
With any calculator, do you also mean graphic calculators?
Yeah, I really don't care. I promise you I can set a midterm where having a graphing calculator is not going to help. And that is my intention.
It's a promise.
Okay, but which sounds ominous, and you're all like, oh my gosh, he's going to kill us. No, I just want to test that you actually have learned something. That's what I'm going to do. I'm going to test that you've learned some stuff. In terms of difficulty level, probably somewhere between the online quizzes and the tutorials. So the tutorial has some challenging questions, because otherwise, you'd be bored. But really, my goal here, we have to do some form of assessment. And that assessment has to check that you've learned something, and that's what I want to do. Yeah, but I'm not going to break you. All right, so what are we up to today? So we need to finish off a little bit of work from chapter 12. So we've been talking about derivatives of functions of 2 or 3 variables. And we're going to learn about a really important thing that's just going to keep coming up again and again and again, which is the gradient. We're going to talk a little bit about applications of the derivative, not a lot, And a lot of it is stuff that you can, once you know how to optimize in Calculus 1, which you've already done, applying what you know to functions of more variables is pretty straightforward. So I've pulled out this section, 13.3, which is applications of the derivative Lagrange multipliers. This is a technique of constrained optimization. It's not difficult. If you ever need to do it, you can learn it very quickly yourselves. And we don't really have time for any additional things. We don't need it further on in the course, so we're losing that. Then we skip merrily away from derivatives and head into the world of integration, because obviously we just learned how to take derivatives of functions of many variables. Now we need to know how to integrate them. Hooray! But the good news is we're really only going to focus on integrating functions of two variables, which gives us what are called double integrals. So 14.1 is just kind of an intro. 14.2 says how you actually do this. And this here, we are kind of looking specifically at definite integrals. We'll talk a little bit about indefinite integrals, but not a lot. Improper integrals, so what happens when you have limits that are going to infinity? The same sorts of things that happen when you have a function of one variable. You have to think about it. And if we're lucky, we will get to polar coordinates. So I'm not quite sure how far we'll get today. And I'll base the tutorial and obviously the midterm on how far we get today. So if we don't get up to here today, that will not be in the midterm. Okay, so where are we at? If you cast your minds back to last week, we were taking a lot of partial derivatives. And then when it came to finding tangent planes, we were basically using the partial derivative with respect to x and the partial with respect to y again and again and again. And it seems like these things are super useful. So it turns out to be very handy to have kind of a thing which encapsulates that information in one place. And that thing is called the gradient vector. And we'll talk a little bit more about it, but what is it? Well, the gradient of a function f of xy is simply the partial derivative with respect to x in the I direction plus the partial derivative with respect to y in the y direction. Okay, so the first thing to notice is here we're only talking about a function of two variables, so something that takes in an x and a y and gives you a surface. So that's we will extend this, but at the moment that's what we're talking about. And what we get out is a vector that lives kind of in the xy plane. It has x and y coordinates. Okay, we're going to look at its what it does in a moment, but just a few more bits of information. So if you think back to the very first lecture, I said that there were a bunch of things. In fact, maybe I can find it here. Where our main goal was to be able to understand Maxwell's equations. And you'll notice that now, finally, we've got one of the symbols that we needed, which was this thing over here. So that's our grad thing. Okay, so we still haven't really talked a lot about, so we don't know about dotting grad with things, but we're getting there. Okay, so we've got that symbol that we've been looking for, which is delightful. So we can talk about the gradient of a function, and that's just the rate of change in the x direction, rate of change in the y direction. But we also think of this thing as living in its own kind of little world, and we call it an operator. Now you mightn't realize it, but you've actually encountered operators quite a lot before. For example, if you want to find df by dx, you think of this as the derivative of f with respect to x. But another way to think about it would be saying, take your function f and do the thing which that funny d by dx thing tells you to do, which is take the derivative with respect to x. So really, every time you differentiate, you are in fact using an operator. You are applying the differential operator to your function. And similarly, when you integrate, you are applying the integration operator to your function. An operator is just something that says, do this operation on the thing that you're applying it to. Yeah?
But is that just for 2 dimensions? So is that like the right form, or we don't have that dimension? I mean, for this formula we don't have
So as I've said, we're at the moment just looking at a function of two variables, in which case we define the gradient to be this thing in two.
But if it is the function of two variables, it is like already in three dimensions.
Yes, but it is a function of two. It only changes in, it has two independent variables that you're putting in. See where we go with this? Okay. All right. So, and as I've said, we will define it for functions of three variables, but for the moment for two variables, this is what we've got. And it is a little bit weird because, as you say, functions of two variables live in three space, but this is something that just lives on the xy plane. But you'll see when I explain what it tells us, why we do it like that. So if we think about our del as an operator, or our grad as an operator, it looks a little strange. We take away our f there and we end up with this symbol over here, which is an upside down delta, which I will mostly call it del because that's how I learnt it. But you might also hear it called nabla. So for example, my Russian maths lecturer always called it nabla. And I always had this vision of like this little grim thing that was like rushing around being like all nabla. Okay, but I will call it del. And what is it? It's a little strange. It says, if you apply this to a function, what you end up with is the thing that we saw over there, the gradient there. But what it says is, if you apply this to a function, it says, okay, calculate the partial with respect to x and make that your x component. Calculate the partial with respect to y and make that your j component. So this thing kind of creates a new vector for you. And as you'll have seen from our quick check back to our first lecture, we are going to often treat this like a vector, so we're going to take cross products of other vectors with it and dot products, but at the moment we're just applying it to functions of two variables. Okay, so it's going to come up all over the place. Okay, so what is this thing? How is it helpful? Take a moment to please find the gradient of f of xy where this is our function. And maybe take a moment to think about what kind of a surface is that function? Okay. So talking through quickly, what kind of a surface is that? Hmm? Okay, it's got squares in it, so it's not a plane. So I want to know what surface f of xy is.
F of xy, it's
Hmm?
isn't it like a paraboloid?
I'm hearing paraboloid. What else? Okay, so if you want to think about this and say, okay, what does this bunny look like? Firstly, I would recommend drawing it in GeoGebra. But if you don't have that, how do you do it? Well, remember we've talked about cross sections, things like that. So if you look at it, if you say, okay, if I hold, remember that this is really z is equal to x squared plus y squared. What can you tell? Well, if you hold z at different levels, for example, 0, then it's going to be 0. If you hold z at 1, then you've got 1 is equal to x squared plus y squared, which is a circle. If you go z is equal to 4, it's another circle, but it's bigger. So if you're chopping it this way, you're kind of getting increasing circles.
So it's like a cone.
So it's a cone, not quite a. Okay, so it might be a cone or a parabola. Both of those would work. Okay, now let's imagine chopping it this way. So, for example, I'm letting y equal 0. Then what do I get? I get a parabola. So if I chop it this way, then I'm getting a parabola. So it must be a parabola. Okay. And in fact, let's just have a look. There it is. Okay, there's our parabola. Okay, so going back, so first partial with respect to x is 2x. Okay, and I want to evaluate that. Okay, so we've got df by dy is 2y. Okay, so del f, or gradient of f, is equal to 2xi plus 2yj. Okay? And if I particularly want to evaluate it at the point 1, 2, now I just plug in x is equal to 1, so that's going to be 2i plus 4j. Nice. Okay, so that's delightful, and we did a bunch of calculations. What is this thing? Well, I'm going to head to GeoGebra so that we can have a look at it. So if I plot the vector that we just found, which was, what was it, 2i 4j?
Yeah.
If I plot that on the xy plane, I get this vector here. So if I started at the point 2, 1, that's the vector there. Okay. What does it do for us? Well, what it tells us is that if I start at this point and I want to find the fastest way to increase up my parabola. So I'm thinking of, actually I'm starting on, that point on the parabola. And I want to know which direction should I go in order to increase as fast as I can. The direction I should go, the way in which I should increase xy is in that direction, which makes sense because you want to go straight up. So as I go in this direction, my z will change as fast as it possibly can. Does that help a little bit? So now you can see why we have it in the xy plane, because it says change your x and y along this way to change your function as fast as you can. Does that help a bit? So if we go back to this, another useful way to look at it is if you look at the level curve, so again, we're looking, so now I'm looking in my xy plane, so my parabola is coming out like this, and I'm looking when x is 1 and y is 2, and I plot my vector that we just found. And the other thing that you'll notice about it is that it is tangent to my curve at that point. I mean, sorry, not tangent, perpendicular. So it is perpendicular to the tangent line. Okay. Questions? So we will end up working a lot with this vector, and you will get more and more used to it. But for the moment, the things to take away are that it lies in the xy plane. It doesn't have a z component. And what it tells you is if you move in the direction of that vector, then, so if you increase x and y a little bit in that direction, it will increase your z in the biggest way that you can. So you never needed this when you were studying calculus in one dimension, because you were always, if you had a function like this and you worked out the derivative here, then you knew immediately that if you made a small change in x, that would give you the fastest change in your function. We never needed anything to tell us which direction to go in. But now we do, because we're in at least 2 dimensions. All right. So I'm actually going to pause there. Any questions? Yeah.
So the factor you get from the gradient tells you in which direction the slope should change, or sorry, can you just briefly summarize it?
Sure.
Yes.
So let's go back here, and let me try and not zooming in. Okay. All right. So I suppose the question that we're wanting to ask is: suppose I'm at the point 2, 1, and whatever the z is up there, and I want to know which way do I go in order to get the fastest increase. Well, I depend on x and y, so you need to tell me how I need to change x and y. Do I need to go a little bit negative x? Okay. And our gradient vector tells us that. It says, in this particular case, you need to increase both x and y a little bit, and if you do that, you will climb as fast as you can up your surface. Does that help? Okay, it feels a little bit weird because it feels like, well, if I head in this direction, I'll hop off the surface.
Yeah.
But remember that if I increase x and y a little bit here, my function z is equal to x squared plus y squared is going to increase as well, and it's coming out at me. So if I increase there, I will climb up. Yeah? Yeah? Okay.
So, like, a real life example of this would be, in which direction does an airplane need to go so it can...
Yeah?
So it can reach a certain point as fast as it can? Or
Right, so any of the kind of things where you're wanting to ask, how do I get somewhere the fastest? You would use this.
Okay.
Yeah.
And what we found is essentially the vector is perpendicular to the tangent at point 1.2.
Yes.
Okay.
Yeah.
Good.
And in general, if we go back to our... So over here, we have an equation for the vector which lies in the xy plane and is perpendicular to our function at whatever point x and y you put in. We happen to put in 1, 2, and so we got this. So this is, I mean, the equivalent in calculus of one variable is here you've just found the derivative, and over here you found the derivative at a point. It's just we're in vector land now because we've got too many dimensions. Okay. So that's great, so this tells us which direction do you go in, which x, y how do you change x and y to increase as fast as you can. But sometimes you want to ask a slightly different question, which is, if I go in blah-de-blah direction, how much will my function increase or decrease? And so to do that, we have what we call the directional derivative. So sometimes we're wanting to find the rate of change in a different direction. We want to, find out if I'm busy producing something that takes in inputs of 2 different things, and I want to know I'm going to increase my production by so much, like how much will it change? So the thing to remember here, we're going to use the dot product. So if you have 2 vectors x and y, so got an, oops, there's an x, no, that's not a good one. There's an x, and there's a y. One way to interpret the dot product, which I hope you've seen before, is I can imagine, so now imagine that I've got the unit vector in my y direction. And my dot product here really tells me what is the component of x in the y direction. So my dot product here, so this over here is x dotted with the unit vector in the y direction, so that's just a number, and that's in the y hat direction. Does this seem familiar?
Mm-hmm.
Yeah, okay. And we are conveniently going to use that straight away to say, well, okay, we know that if I go in the direction of my gradient, I'm getting the most change that I can get. So if I want to find the change in some direction that's slightly different to that, if I take the dot product of the direction, the unit vector in the direction I'm interested in, with the direction of maximum change, I will get the amount that I will change if I go in that new direction. So my directional derivative, which I write as d subscript u, and this is a vector, so usually if I write it, I will write it as du with a hat. So this says, if I move in the direction of u, sorry, that should be a hat. Not a, should be a hat. This says if I'm on my surface and I move, if I change my x and y according to this little unit vector here, so I move a little bit in the u direction, how much will my function change? It will change by this much. Okay? So I think it's more straightforward if we actually just have a look at some examples. So let me pull this here. Okay, now the key thing here is that this needs to be a unit vector. So if you're asked to find the rate of change in each of the following directions, first make sure that this is a unit vector. If it's not, turn it into a unit vector. Okay, so you've got a couple of calculations to do. So if we have a look at this, we need our gradient. So our del f is going to be what do I just do here? I think. Let's just quickly check. So I'm firstly just working out my gradient of my function. So I need the partial derivative with respect to x. So first term nothing, second will be 2y cubed, I think that's right. Now derivative, so that's a 2x y squared. Okay, I'm fairly confident of that first term. Yep. How did I do on the second term?
4y cubed.
4y cubed, yes. Okay, and the rest? Rest of it, okay?
Good.
Yep. Hooray, okay. But I'm particularly interested at the point 0, 1, which is a nice point because I get to have a whole lot of zeros. So that's going to give me 2i plus 4, maybe? Yeah, okay. And then we won't do all of these, but what I need, so I'm saying u is let's call this u1, is the vector I plus 2j. Is it a unit vector?
No, you divide it by its map.
Grr. Okay, so if we want to turn it into a unit vector, then we just divide it by its magnitude. So it's going to be an I plus 2j over square root of 5. So I'm actually just going to okay. So now if I work out okay, so if we do this calculation, I should have I think, yep. So what,
Yeah.
yep. Okay, so what is this telling us? Who knows? Okay, what it's telling you is that if I make a unit change in the direction of this unit vector, then overall my function, my z value, will change by this amount. So this is getting what we have very easily in calculus of one variable. If you know that the derivative at a point is 2, this tells you that if you change your x by 1, your y will change by 2. Here, this is telling us, finally, that if we move in that direction, then our z will change by this. Yeah? Okay. So what I would recommend that you do for homework is work through the other examples, and you'll find that the situation where, so we found that our gradient is in the direction 2i 4j. If you go perpendicular to that, then you're going to find that you don't have any change at all. Why would that make sense? Well, if you go back to the picture that we had over here, we've said, if we're thinking about this function over here, if you want to increase as much as possible, increase your x and y going in this direction, which was perpendicular to your surface. You can check and see from the examples that we do, if you move perpendicular, then you're actually just moving along the level curve, so you're not increasing at all. Okay.
Can you repeat that, please?
Sure. So our gradient says, which way do I go to increase the fastest? And it says, well, you need to actually basically go straight up here, which is equivalent to increasing your x and y a little bit in this direction. But suppose we went in a perpendicular direction. What would happen then? Well, if I think about what's happening up here, I'd be moving along this level curve. And if I move along a level curve, my z doesn't increase at all. Yeah. So you start to see the power of what's happening with our gradient vector. It lets us do a lot of things. It lets us find out which direction do we go to increase the most, but it also helps us find out, if we don't want to increase, which direction could we go in. So please plot all 4 vectors on the xy plane and think about what they're telling you. So you're also going to want to also plot here. I would recommend plotting del f. Yep.
Could you repeat the interpretation of the value we found earlier?
Sure. So what the value that we just found over here, maybe the value that we found here says I'm on some surface, and I don't actually know what this surface looked like. It's some crazy thing. I'm at a particular point, I'm at the point 0, 1. And this says if I increase, so if I change my x and y according to that little u1, so I go a little bit in the x direction, a little bit in the y direction, so I'm changing my input value slightly, what will happen to my output? My output will increase by 10 over root 5. In the same way that if you're in a function of one variable, you know, if you know the value, so your slope is, your tangent at, well, your derivative at a point is 2, you know that if you change your x by a little bit, your y will change by 2. Yeah. Okay.
I'm sorry, I just plotted the first thing that we did.
Yep.
And I just basically get like a big line and then a little line. What does that tell me?
Okay, so you got something. Well, let's do the first one. Okay, so let's plot 2 plus 4. Okay, so that's 2 plus 4.
Mm-hmm.
Okay, so there's. Okay, so that says that's the direction you need to go in on the xy plane if you want to increase maximally. Over here we found 1, 2, so that's in the same direction.
Okay.
As in, is that what I found? 1, 2. So if I go 1, 2, it'll be here. So this tells me that if I go in that particular direction, which happens to be the same direction as my directional derivative, I will increase by 10 over 5. So let's actually do one more, and you'll see the difference here. So let's find which one should we do? So let's do number 2. So if we take, so that's minus 2, 1. Minus 2, so that's okay. Now what happens if we take the dot product? What do I get? I get a 0. Okay. So now let's plot this vector over here. So that's minus 2i plus j. I'm not worrying about the scaling. Well, if I plot that vector, it's going to be 2 minus 2 plus 1. It lives there. So this tells me that if instead of going in this direction, which is the direction of my gradient, if instead I go at right angles to it, how much change do I get? I get 0 change.
Thank you.
Yep. So I think that was a useful thing to do. And if you have a look at U3 and U4, they'll be in between, and you'll get numbers that lie between 0 and 10 over root 5. Yeah.
Is there a way to determine given a given directional derivative? So if it is the greatest possible one without comparing the vectors? If you're just given a directional derivative, can you determine like if
No,
it's-
because you're going to need your gradient because that tells you.
Okay, yes, so
Yeah.
you have to always go back.
Yes, yeah. You're going to have to do another calculation, and the quickest one is just find the gradient. Am I in the same direction? Yay. Am I not? Boo. Yeah. Okay. Did that help a little bit? Yeah. Okay. So now, if you're asked in a test or exam, by how much will my function change if I move in this direction, you know how to do it. Okay.
So then question, how do I know how much my function changed if I'm moving along the gradients? Because round gradient is vector.
That's a great question. So
I can just
yeah.
do the dot product between the gradient and the gradient itself, and then I got
Exactly.
Yes.
Yes.
Okay.
Yeah, which is actually what we ended up doing here. I just didn't tell you.
Ah, okay.
So the question is, okay, so how do you know what your maximum change is? We know the direction. What is the maximum change? Well, you want to find the maximum change in the direction of the gradient. So what you would do is you would take your gradient, so your max change will be, you want the unit vector in the direction you're interested in, which is the direction of the gradient. So it would be your 2i plus 4j over whatever so that's 620, root 20, maybe? Root 20 dotted with del f at 0, 1. And that tells you how much you will change if you go in the direction of maximum change. Feels a little weird. It looks kind of complicated. There you go. So I would double check that if you do this calculation, you should still get the same answer that we got over here.
What? No.
Yep.
I just don't understand it. Like we are by dividing by x we're finding the unit vector,
Mm-hmm.
and then we are multiplying by this gradient again.
Yep.
Maybe you want to get number, so you need to have a dot. But yeah. Otherwise, you don't have a vector.
So
The dot product is a scalar instead of vector. Question.
Yeah.
If I want to have this in, say, what would happen if instead of having an input for this f, so this gradient of f, say in this case 0, 1, if instead of a point, I just take the variable form, so f, x, y. Can I still get a general expression for this?
Yeah.
Or, okay. Just wanted to know if that's legal, mathematically.
Legal.
Yes.
Yeah. I mean, so then you would end up with something over here, which has x's and y's.
Yeah.
And that is
Yes.
essentially telling you, depending on which x and y you put in, how much your function will change if you move in that direction.
Perfect. So in this case, we would get 2 over square root of 5x plus 8 over square root of 5y.
Yeah.
And you can
Yeah.
just leave it.
All right, how are we doing? Yeah?
Could you find the U2 in the figure we had before? No, the one in 3x. Is that the same function?
No, it's not the same function, but I can plot it. You want me to
No,
plot
it's
it?
okay. It was confusing because I thought it was the same function.
Ah, no, it's not. Sorry. Okay, so what I will do in the final notes is I will get GeoGebra to plot that function for me. And then I'll put those vectors on and you can see and play around. Maybe that'll be helpful. Yeah? Okay.
But will it be just the length of the vector of the gradient, like how much it
Yeah.
will change? Actually, just
Yeah.
Sorry, could you repeat again the logic behind the maximum change?
Let me see where I should go back to. So the logic without, and this is a bit hairy because I haven't proved it to you, so you're going to have to trust me. But in a function of one variable, if you have a change like this, you know if you find the derivative that if you increase in your x direction, that will give you the maximum rate of increase. It's the only rate of increase, but it is the maximum rate of increase. And the reasoning goes that if you do that in x and y, so you find the maximum rate of increase in the x direction and the y direction, in order to get the overall maximum, you combine them into this vector.
Okay, so that's why you need the dot product.
Yeah.
Okay, yeah.
Yeah.
Okay, got it. Thank you.
Okay, so let's just look at a few more examples. So here I'm thinking about a good old sphere. So an x squared plus y squared equals 1, so a sphere of unit radius. And if you feel like it, you can go ahead and you can find the partials and hence create your gradient vector. And let's think about what it's telling us. So, for example, if I think about the point 0, 0, what happens? So our gradient vector says go in this direction if you want to increase as much as you can. Now I'm thinking about this point over here at 0, 0. If I plug in 0, 0, what happens to my gradient?
I got 0.
It's the 0 vector. What is it telling us?
That's the maximum.
Right, it's saying, sorry, you're doomed. If you want to increase, you can't. Okay. But on the other hand, if we looked at, for example, at a slightly different point, so we're looking at this point B over here, if you calculate your gradient vector, it says, okay, if you want to increase as much as you can, you need to go a little bit negative in the x and y. Think about what that means on your sphere. We know that you want to move up that direction. And in order to do that, to go up here, you need to decrease x and y a little bit. So it is now telling you, so your gradient is now saying to move here, if you want to go up as fast as you can towards the pole, then you need to go a little bit at negative x and negative y. Yep. So I really would encourage you to use GeoGebra to plot these things.
This is mind twisting.
This is mind twisty. Okay.
Yes.
It's not supposed to be easy. If you're feeling uncomfortable, that's great. Okay. All right. So, what have we got here? Properties of the gradient vector. At a particular point, our function increases most rapidly in the direction of the gradient vector, by which we mean that if you change in that xy direction, your function, your z will change as fast as possible. And as we've actually just seen, as was pointed out, the maximum rate of increase is this thing over here, which is what you get if you drop the unit vector in the direction of your gradient with your gradient. You just get the length of your gradient. So the quick version of how do you find out the fastest, the amount by which you can increase fastest, take the length there. And similarly, if you want to decrease really quickly, go in the opposite direction. And the fastest you can decrease is the opposite of the fastest you can increase at a particular point. And if you happen to shimmy along a level curve, then as you would expect, your function doesn't increase at all. Okay. So you'll be delighted to know that we can extend this to as many dimensions as you would like. We're not really going to do that a lot, but the reasoning is exactly the same. So for a function of 3 variables, so we're thinking of something that takes in an x, y, and z and gives you out another number. So if you plotted this, it would be in 4 dimensions. You could ask the question, which x, y, z direction should I go in order to increase as much as possible? And this is not an insane thing to do. For example, you might have a temperature map for the temperature in this room. That is a function of 3 variables because you'd put in a point x, y, z and you'd get out a temperature. And if you're feeling really chilly in the room, you might want to know which direction do I go in order to get warm as quickly as possible. Well, that will tell you. Okay. And in fact, if you take its length, it will tell you how much you can expect to warm up as much as possible. Okay. But we've just extended this by a single variable. Okay. All right. So I'm going to leave this as an exercise for you to do. It's just working through things, so it's just finding your directional derivatives. Finding your gradient. So the one thing here that is interesting is now we have a much quicker way of finding, or a kind of a routinized way of finding tangent planes. Because up to now we've been saying, okay, well, if you want to find a tangent plane, you have to find the partial derivative and then create that vector. And then you have to find the partial in the other direction and to create that tangent vector, and then you have to cross product them. But actually, all of that information is encapsulated in your gradient. You just need to add on an extra term. So you can think about that. So there's even a picture here that will show you what you're doing here. Okay. Phew. So please spend some time not only just calculating gradients, because that's just kind of boring mechanical stuff, but actually plotting things and building up an intuition for yourself of what your gradient vector is telling you. And similarly with directional derivatives. We can use what we've been doing now to think a little bit. So if you think back to what you did in Calculus 1, you spent a lot of time learning to calculate derivatives. And then the whole reason to do this was to be able to do things like, for example, optimize functions, find maxima, find minima, and surprise, surprise, we want to do the same thing for functions of more variables. And it's going to turn out that up to functions of 2 variables, it looks very similar. So just to remind you from Calculus 1, how did you find maxima and minima? Well, the first thing was that you needed to find all the places where it might potentially be a maximum or minimum, and then you had to rule out cases where it wasn't. So where might you have a maximum or a minimum if you're a function of 1 variable? Well, critical points, so points where your tangent was flat. Singular points, points where you don't know what's going on with your derivative. And endpoints. So it could be that you have something, a function over here, that might be a maximum or a minimum. Okay. And pretty much the same intuition is going to apply when we talk about functions of many variables. And just to remind you, you would have done a first derivative test and a second derivative test. Mm-hmm. Okay? They're coming up. So if we're thinking about functions of several variables, in particular 2 over here, we can also think about how do we characterize places where we might have a maximum or a minimum. And in fact, we just use the gradient, and it turns out to be very similar to what we had before. So for example, a critical point is any point where our gradient is flat. So we already saw that when we looked at the sphere at the top, where we couldn't increase any more because it was a maximum, our gradient was 0. And you can imagine that if you were looking at a bowl and you were looking at the bottom over here, your gradient would also be 0, which would be telling you that you were at a minimum. So in terms of checking for critical points, instead of solving where is my first derivative equal to 0, you just solve where is my gradient equal to 0. Remember, that's not guaranteeing that you have a max or a min. It's just saying you might have one. So you might have some weird kind of saddle point that you've seen before, but it's a possibility. Similarly, we need to think about points where our gradient doesn't exist, which we haven't really talked about, but don't worry too much. And again, boundary points. So if we're thinking about, for example, something like this, if we're finding all the maxima and minima, maxima is one within our region, but we might have minima around the edge. Okay, so the only thing really that's changed over here is that you're using your gradient, not your first derivative. Yay. So that identifies likely candidates, and then you have to do a little bit more in order to check if they actually are maxima or minima. So just to give you pictures of the kinds of things that are equivalent to the one-dimensional things that you'd work with, minima, maxima, but you can also have saddle points. So here we've got a minimum in the y direction, but a maximum in the x direction. So that's the kind of thing we need to guard against. And similarly over here, we don't have a maximum or a minimum in either direction, but at this point our gradient is flat. So now we need some way of kind of dealing with those.
Just a quick question.
Yeah.
It's just a curiosity question, but would taking the Laplacian that tell you if it's a minimum or maximum or no?
Laplacian is not the same as the second derivative.
Yeah, it's a
not
dot, it's a dot of the gradient.
not quite. Yeah.
It's the gradient dotted with no, I'm gonna stop. Yeah, I'm gonna stop. It's not the same thing.
Yeah, the Laplacian is a really tough.
Yeah, but it's not the say anything and
Yeah.
gives you a scalar.
Okay, so, okay, I'm just gonna pause you there. By all means, go and check it. See what you find out. Okay, so how do we, okay, so we've got these candidate things. We want to find out, are they maxima or minima? How do we do that? Well, one way, which is kind of annoying, but you could do it, is to just see if you go in bunches of different directions from your point, what happens. And if you hopefully did enough points, then you could make a valid guess. So that's, and that was always the case with Calculus 1, you could do that too, which is frustrating. Okay, we don't want to do that. We would like some solid way of doing that. And it was the second derivative test that gave you a fairly solid way of determining if something was a maximum or minimum. From calculus of one variable, you did a bunch of things like that. Look familiar?
Yeah.
Okay, so you found your first derivative, and if it was equal to 0, you looked at your second derivative. When was it less than 0? It was a local max, bigger than 0, and so on. For functions of two variables, we have a similar looking thing. The things to note here is that this is a critical point. So going back over here, we're only looking here at points where our gradient is equal to 0. Our second derivative test doesn't help us if we're a singular or boundary point. Okay, so that's the terms and conditions. But we use a combination of second derivatives, but second partial derivatives. And we do this weird check. And if you're seeing a b squared minus ac, and you should think this sounds familiar, there is a link to the discriminant, but I'm not going into that. Okay, for the purposes of this course, I am telling you that if you have a critical point, so your gradient is equal to 0, and you calculate this weird thing, b squared minus ac, where a, b, and c are given like that, then if your a is bigger than 0, and this is less than 0, you have a local minimum value. Okay, so this is a kind of annoying table that I would recommend that you write out, and I'm very sorry that I'm not proving it to you. I would love to if you come to my class. I mean, if you come to my office sometime, I will. But as far as we're concerned for this course, this is how you test if you have a maximum or a minimum. Okay.
Is it going to be on the formula sheet, or something that you're kindly advised to write on our sheet of notes?
I will check and see. I will try and put it on the formula sheet.
It does not fit.
Yeah.
No. Okay.
Okay. So, okay. I'm going to show you something. Don't panic. This is for interest only. It's not examinable, but if you've done linear algebra, then this will give you some of the background that you need for this. Actually, it's okay. The second derivative test in general, so now we're looking for functions of however many variables you're feeling like it. The second derivative test requires that you create what's called the Hessian matrix, which is a matrix that contains all the possible partial derivatives. So if you're a function of two variables, you just have the first 4, f11, f12, blah, blah, blah. But if you're a function of 100, then you'd have 100 by 100. And it would be delightful. Okay, so this is called the Hessian. And one thing to note is that because our partials are, so when you've got multiple partials, they're interchangeable. This is symmetric. Actually, what we're saying when we do the second derivative test is that if our Hessian is positive definite, then we have a local minimum, and so on. At which point you might be like, well, okay, that's great. What is positive definite? And for that, you need to know about quadratic forms, eigenvalues, and eigenvectors. Okay, you do not need to know this for this course, but if you've done some linear algebra and you've done all of this, then you can see from all of this how we got the equations on the previous page. Okay, that's what I'm saying there. Okay, so what do we need to take out of the things so far today? You need to be able to calculate your gradient, and you need to be able to calculate directional derivatives, and you need to be able to maximize or minimize functions of two variables using the second derivative test, or tell me that you can't because you found that the gradient is not defined at the point I've asked about, or it's a boundary point, because I haven't taught you how to deal with those. Okay. All right, 3-minute break. Get up, stretch, do whatever you need to do, and be back by 5 past, please.
More lecturers should do this.
You mean teach multivariate calculus?
Yes. Yeah.
I think so too.
That's what I think.
I mean, they could try, but conveying it pedagogically good is not gonna be easy. Yes.
Yeah, it's tricky.